Right. The purpose of this video is to look at how to do the quantitative error analysis. And so I'm going to kind of walk through the process, and then I'm going to model how to do it using the data that is in the prelab. So what we would need to do is, again, if we kind of refresh ourselves over what this actually entails, you can see that on the lab report page, we have here a document that talks about quantitative error analysis. And so we'll open that up right now. And what this is telling us is what are the tolerances for the given pieces of equipment. So if we use an analytical balance, for example, an analytical balance is going to give us a mass. Let's just throw one out here. It's going to give us 0.3482 grams. Well, what the tolerance tells us is that if I'm looking at an analytical balance, that reading 0.3482 has a little bit of error attached to it, 0.1 here in that last decimal place. And so when we do error analysis, that's what we are looking at. We're looking at how does that little bit of wiggle room at the end of that measurement actually impact our ability to interpret the data and interpret it with accuracy and precision. So there are error bars, there are tolerances associated with each kind of piece of equipment that we have. So if we are looking at doing a volumetric analysis, which we'll do later on in the semester, there's going to be more of these because you're going to have burette readings. You're going to have pipettes that you're using to transfer the liquids around. Maybe you're making solutions in volumetric flasks, or you're using graduated cylinders, or maybe we're doing temperature and pressure kinds of views. All of those would make a difference. Now, in our case, it's actually really simple. We only dealt with the analytical balance as far as equipment is concerned. So we only need to, in this case, focus on this part of the analysis. And in particular, we can actually simplify this a little bit further because every single mass that we took was based upon a pair of readings. I measured the mass of the crucible, and I measured the mass of the crucible with something in it. And the difference between those two was the mass of my stuff. Well, this is no different, right? I've got this mass and I've got this mass, and I'm going to do that, however many times. So in this case, that's really the only piece of equipment that we have to worry about. The other thing that we would want to worry about are what we call assay limits. These are purity standards. So if I'm looking at the solids that I'm using, we can assume that they're relatively pure, but they might have some impurities in them. And so when it comes to these assay limits, we're looking in two directions primarily. So there are what are called primary standard reagents. Those are nearly 100% pure. They're 99.99% pure. And we don't tend to use those very often. They're expensive to get a hold of. And generally, we just don't need that level of precision. That's more of a research grade thing, or if you get into analytical chemistry, that's kind of the place where you'd see some of those. We tend to use reagent grade chemicals. Reagent grade chemicals are 99.5% pure. And for our purposes, that's pretty good. That's good enough. So with that, though, we do have to take into consideration that 0.5% of those copper atoms potentially may not be pure copper. They might be copper oxide or some other compound. And so we got to take that into consideration because that's obviously going to affect the ability of our copper to react purely. Same thing with the sulfur. A little bit of variance in there, that's going to play into the role as well. And so we would want to account for that in our analysis. And so when we go to do the analysis, then again, I'm going to pull up our prelab as an example. What I can start to look for is I can start looking for, well, what are the pieces and parts here? So I have a mass of product. I have a mass of vanadium, and I have a mass of sulfur. Now, and then I also would have a mass of the vessel. We can assume it's a crucible in this case as well. So what are the relationships between all of these? Well, the mass of the product isn't as important to us because that's important to the secondary analysis where we're doing the mass percent calculations. But in terms of the empirical formula itself, we are looking at the mass of the vanadium and the mass of the sulfur. The mass of the crucible is important to that because when it comes to the setting up of this, we would be looking at, how did I get this? I got this when I took the mass of the vanadium plus crucible minus the mass of the crucible. So I had two readings going into the calculation of this value. And for the mass of the sulfur, I could look at the mass of the product minus the mass of the vanadium plus the crucible. And that would have given me the mass of the sulfur. Again, two readings involved here. So when it comes to calculating the error associated with these two values, well, now I can start to look at, okay, the error associated with the mass of the vanadium. Well, I did two readings, so that would be 0.0002 grams. Each one would have had a tolerance of 0.0001. So since there were two of them, 0.0002. And I would divide that by what is the actual mass of the vanadium? It's the 0.3268 grams. So divide those two, multiply by 100. And so if I do that, 0.0002 divided by 0.3268 times 100%, I get 0.06% as the error that I could associate with the mass of the vanadium in this particular trial. I could do something similar for the sulfur. Again, it's based on two readings, so 0.0002 grams. The mass of the sulfur we determined here is 0.5101 grams. So if I take 0.0002 divided by 0.5101 times 100%, I get 0.04%. So I'm not getting a whole lot here out of the masses in terms of error. The only other error sources that I can begin to look at and account for then would be, okay, what is the purity of the vanadium? Well, the error in that is up to 0.5%. And what is the purity of the sulfur? Well, that's up to 0.5% as well. And so if I add up all those together, the total error for this trial would be 0.06 plus 0.04 plus 0.5 plus 0.5, 1.10%. So if I did a second trial, which you did, you would need to do this calculation again. You need to do it for the second trial using your masses in the second trial. The purities would be exactly the same though. So that's basically what you're being asked to do in this set. As far as sig figs are concerned, you really only need one significant digit out of this calculation here, because that's all that the tolerance gives us. That's why we rounded here to those digits there. Once we add, notice that each one of these comes out as 2 decimal places. So our error came out to 2 decimal places as well. Now, one thing that we need to know as far as the analysis is concerned, we want to compare this value, the 1.10%, to the value that we calculated here as our percent error. Percent error in this case was 0.49%. And so what we need to do is we start to look at this and say, okay, that 0.49% error, is that satisfactorily explained by the error analysis that we just did? And so if the percent error here in our calculation that we did as part of the experimental analysis, if this calculation is lower than this one, then that's a really good sign. What that is saying is that for the most part, we can probably assume that the errors that we're seeing here, this 0.49%, can probably largely be explained away by the instrumentation that we used and the purity of our solids. If this number is greater, then we have to start looking at the actual data. And we need to start looking at, well, did we do everything that we were needed to do? Can we start to look at this relationship between what we got experimentally versus what we got theoretically from our empirical formula? And in most cases, for most of you, what you're going to find is that your ratios, most of you got a ratio of 2 to 1 for the copper to sulfur. What you'll find, though, is that you usually had to round that up. Most of your actual calculated ratios were somewhere between 1.7 and 1.9. And so depending upon how close you were to 2.0, your percent error kind of varied a little bit. Now, what does that say? Well, if the compound itself is actually Cu2S, what that says is that you had extra sulfur in your crucible at the time of weighing. Where did that extra sulfur come from? Well, it could be that at kind of the microscopic level, you didn't burn off all the sulfur. And so you would need to go back to the procedure and say, okay, did I do the procedure as well as I could have? If I were to go back and do it again, would I look and do it something different this time? Because that's really what it comes down to, is comparing your data versus the theoretical and trying to find realistic, tangible ways that you could have made things different, made things better upon repeating the experiment. And so this error analysis helps us to see just how deep we have to go into that conversation. One last important note. These errors that we are calculating here, they are a bit of an overestimate. You know, we're taking a little bit of liberty here saying that the full amount of the error is 0.5% for each of those substances. It's likely lower. But since that is the assay limit of the substance, we're going to kind of take on the worst case scenario there and say that the substance reaches that assay limit. Again, chances are pretty good that if we're using, good quality chemicals and they're relatively fresh, chances are pretty good that 99.5 is on the low end of what actually it is. It's probably a lot closer to 99.9 or 99.8. And so you can see that in this estimate, we're probably overestimating a little bit. So that's all for this video. If you have any questions, please feel free to ask. Send me an email, send me a chat message. I'll try to help you as best I can, but really try to do this analysis, especially since it's so simple. Try to do it for your rough draft. It'll make your rough drafts a lot better, and I'll be able to kind of give you more feedback in the moment as opposed to trying to figure it out before the final draft is due. Have a good day.